Hello, this is Samantha that's going to present to us real-time data pipelines. I'm Clarence, and so I'm the room host at this volunteer. And so I'm going to turn the microphone over to her and let's let her get started so she has the whole 50 minutes.
All right. Can you guys hear me okay without microphone? I'm pretty loud. Yeah. Okay. Do it this way. I'm doing a new phases here. I'm turning it off. All right. So yeah, my name is Samantha Quiñones. I'm a principal software engineer at AOL, which I've never heard of. I've been doing software engineering since 1997. Is there a way to maybe dim the lights a little bit? It's a little hard to see.
Let's see if we can figure it out.
Yeah, that's better, right? Okay. So, yeah, I've been a software engineer since 1997. Was in the financial services sector. For most of my career, I moved into media. In 2012, and I've been at AOL since 2014 as a principal software engineer on the media platform team. So, for those of you who aren't aware of what AOL's been up to since the dial-up days, we merged with Time Warner a number of years ago. Then Time Warner kind of like spit AOL back out, like, sick child. And AOL kind of became a media company. So AOL actually owns Huffington Post, and Engadget, TechCrunch, all these different media properties that you guys are probably more familiar with than AOL itself. And the team that I work on runs all the back-end systems that make those products work. When I joined AOL, let's say they reached out to me. I was actually working at another media company, and they reached out to me about joining the company. I was kind of like, no, why would I work at AOL? But I kind of eventually just agreed to take an interview, and one of the interview questions that really struck me was this: how would you let editors test how well different headlines perform for the same piece of content? And that's a really good question. It's the kind of question I like to ask in engineering interviews because it doesn't really require regurgitating any knowledge. It's a question that kind of gets at how someone approaches a problem. And I want you to keep this question in the back of your head for a few minutes because we'll come back to it. The question, or I should say the problem that AOL was having when they brought me on was how to measure the way these applications are performing. And I mean that both from an application performance metrics standpoint, and how they're actually performing on the metal, and how they're performing in terms of advertising revenue and social uptake. Right? So when we look at traditional metrics, a lot of what we do is look at things like response time for requests. How fast are we serving content? What is our cache hit rate? Are we using caches effectively? What is our resource utilization? Do we have enough hardware to handle our traffic or not, right? And there are really, really great tools to do this. We use New Relic for a lot of this kind of stuff. I love this graph. This is really, really old now. So this picture kind of goes from, this shows the CPU request response time versus throughput, right? So over here, as we get kind of lower and lower, the response time comes lower and lower as the number of requests we're serving each second goes up and up and up. Right? So this is a good indication of what? Cache. Exactly. Our caches are warm. Right? So the response time starts to go down. Right? So this is one method that we look at to kind of measure the performance of the application. And we can use these tools for a lot of other things. We can try and profile code. So our stack is PHP. It's a PHP stack for serving billions of requests a month. So if anyone ever tells you you can't build big stuff on PHP, they're lying. But you see, we can see where the majority of our time is being spent in Memcache, in PHP. Web External actually calls to our caching layer. We have a thing called CacheLink. It's actually a really cool open source package. Runs on Redis if you're interested. It's on GitHub. So you can kind of see what parts of the application are taking up a lot of time. It's important to do this kind of performance measurement because the perceived performance of the application is very important to how well it's going to perform in terms of revenue. So if you look at This is it's actually slipped out of my mind where this table came from. It came from it was an O'Reilly book on system performance. But anything under 100 milliseconds, so the human brain is essentially instantaneous. Still a small amount of time, so small. I really drank a lot of coffee this morning. It's an amount of time so small that it's difficult for your brain to perceive it. Between that and about 300 milliseconds, you're seeing a small perceptible delay, but there's no negative attachment to it. And it actually gets up to about 1,000 milliseconds, so 1 second is an acceptable delay for the computer to do something. And in fact, since I worked in financial services, it was not at all uncommon for us to inject artificial delays into processes that seem to be securing information, because it actually gives a perception to the user that the computer's working really hard to make their data safe, right? I'm sure we've all done this, right? It's when we get beyond 1,000 milliseconds that we start running into the perception that the system is slow. And this kind of tails off to about 10 seconds. Now, in 10 seconds, you've lost the user. They're going to perceive your application as being down, just not responsive. Amazon did a study a number of years ago where they looked at latency as it affected sales. And they saw that for each 100 milliseconds of increased latency, sales revenue was decreased by about 1%, right? So for Amazon, who sells, whose revenues are probably in the couple of thousands of dollars per second, having a 1% drop off due to a latency like this can have a severe impact on revenue, and obviously retail margins are tight, right? So this is very, very important. Google also did a study, the search experiment. This was, I think, in 2009, where they looked at injecting artificial delays into search results and found that as those delays got larger, the number of searches performed over a test period went down and down and down. So Google makes their money the same way that AOL makes money. They put ads on web pages. We do the same thing. So this is the number of times we get those ads in front of somebody's eyeballs defines how much money we have, right? And we like money. So latency has a direct impact on revenue. Another important factor of looking at performance is doing A/B testing, multivariate testing, right? So this is where we take all of our users, we sort them into groups. We have a control group that we give unaltered content, and then we have treatment groups that we give altered content, and then we look at those sort of behavioral measurements to see how how that variable affects the user's interaction with the content, right? So we can look at click-through rate, abandon rate, and do that kind of stuff. And then something that's not really often considered part of metrics or performance metrics is state monitoring. So things like exception logging, looking at load, looking at system performance, cache performance, right? So kind of like the operations side of metrics, like looking at how well the application is performing under the covers. What I really want to talk about though a lot is traffic metrics, or not a lot, but traffic metrics are really, really difficult for companies like AOL. We're trying to do things like measure the user's behavior and their experience. So what path do they take? When they enter in one of our properties, how do they move through it, right? Do they follow links, internal links from one property to another? So if we have an article on a gadget that's linking to maybe a longer form piece about the company behind that technology on TechCrunch, are those links keeping the users looking at our ads, right? We're doing mouse and attention tracking, so we're trying to see where on the screen people are focusing their attention. We're doing RUM, so we're doing real user monitoring, injecting some code into the browser to determine what the kind of performance of our like JavaScript and ad loads and stuff like that, right? But how many of you guys have seen this diagram? Okay. This was done by Dreamscape Multimedia a number of years ago. It's kind of very similar to what our heat maps look like, but they kind of show where the attention of people's eyes go on the screen. And it's kind of this F-shaped diagram, and the concentration is up here in the upper left corner. It kind of moves out a little bit to the left, but then it starts going down the page. And if you'll notice, this is laid over Google search results. You can see why Google search results look the way they look. Right? Up here is where the sponsored results are, and then down here are the real results. Right. demographic information. Right, so we're looking at where the users are located. What region is usually what we get, and if we can, actually get the geographic, the latitude and longitude that their person is at. So we can locate them inside of a city, or if they're on a mobile device, kind of where that mobile device was, maybe we're looking at the content, what their ISP was. We want to see what kind of device they were looking at. They were looking at our content with. And then wherever possible, we actually want to try and anonymously identify users. So create this construct of a user. We don't know who that person is, but we know that they were interacting with us over a period of a couple days, or interacting with a couple of our different properties, right? So the AOL Media Platform, which I mentioned very, very briefly when I started, we do content management and distributed rendering farm. This is essentially what all these different properties are built on top of this platform. We have an IDE that uses a custom DSL. It's actually what the developers of these products use, generally speaking. We have a content aggregation platform, so we have all these different content providers and also external providers. We aggregate them together through an API. We have a machine learning platform, right? So we can actually we pump all of our content that we generate into this machine learning platform to try and categorize what's being written about, understand who are the people that are bubbling up in the news, what are the topics that are bubbling up in the news. And like I said, this is a massively multi-tenant system, so we have hundreds of different large properties that are all living inside the system at the same time. What I'm going to talk to you now about is this particular problem, a particular case study of trying to integrate all of this data at AOL, performance measurements, development metrics, traffic metrics, demographic metrics, into a single system that we could use to actually do some intelligence, right? So when I started on this project, we had Omniture, which we still use for all of our revenue analytics. So we're actually using Omniture to try and understand where our ads are being displayed, things like that. We're using New Relic for our APM. We also use ELK internally, so Elasticsearch, Logstash, Kibana, the ELK stack to do performance metrics and log consolidation. And then we have the AOL proprietary data platform, which is called the data layer. I'll probably refer to it as the data layer more often than not. And this is actually where we're collecting all of that run and demographic information. This is I'll talk a little bit about how it's built. This is a massively distributed data collection. It's built on Hadoop, right? So is anybody familiar with Hadoop? Awesome. I see more and more hands go every time I ask that question. That's awesome. So we have this giant Hadoop cluster, petabytes of data that we've collected over time, and you can access it with Hive and Pig, and it's time shared and kind of weird. A lot of that data gets sliced out into Cassandra, so you can we actually have this facility where you can go in and say, I need this particular slices over particular times of data pulled out of Hadoop and put it in Cassandra, so you can get them kind of real-time-ish. We use Vertica to ingest all of that data, raw data from Omniture, and kind of play with it. And then we have a streaming interface for raw data. This is actually what it kind of looks like if you look at it from an application perspective. So we have these beacon servers. If you're on Engadget.com and you have the Chrome Inspector open, you'll see requests that go out to something called b.aol.com or b.engadget.com, and that's actually what those servers are. They're beacon servers. There's nothing spooky or hidden in them. If you look at it, they're just like JSON blobs of data that get sent to these servers. All of this gets pumped into a RabbitMQ farm. And from there, it gets pulled out by the data layer service manager, and it kind of gets buffered into Couchbase as it's coming in. And then from Couchbase, it gets parceled out into Cassandra and into Hadoop, and it gets HDFS, and it goes into Vertica and all this kind of stuff. We have a second RabbitMQ farm, and this is what we call the streamer farm. So all of that raw data, as it's coming in, it gets piped out into two directions. One branch goes into the data store, the data warehouse, and the other branch gets pushed out to these things called the data layer streamers, or the RTA, real-time architecture streamers. These are essentially Java applications, Java streamers, HTTP APIs that you connect to with a set of parameters, and they just start vomiting data at you as fast as you can take it. So this is something, to put this chronologically, these had just been released into production 2 months before I started at AOL. So they're going to play a big part in this story. I mentioned the beacons. Like, this is what the payloads look like. They're often much bigger than this, but there's nothing really that exciting in it. We'll have like the location. We usually get this from the net scalers, so they kind of, when you hit the local edge, we'll get that information about where that happened. We get information about the user agent. This is a multivariate test payload, so I'll talk about that a little bit. The problem with this is that we ingest a tremendous amount of data. So we get about, in each one of these event payloads, we have on average about 40 metrics. So they're actually about 1.6 kilobytes in size. They're big chunks of data. We get 15,000 of them every second. It's about 25 megs of data every second. So over the course of a day, we process 1.3 billion events. It's about 2 terabytes of data. It's very, very hard to do this in real time, which is why we put it into HDFS. You can search for it in using Hive, right? The problem that we run into is that content creators really don't give a damn what happened yesterday, or the day before, or the week before. If you talk to our editors, the people who are actually interested in this data, they want to know what happened an hour ago. They want to know what's happening actually right now, because that's actually the information they need to make decisions about what stories to promote on the homepage. And what should they be tweeting about, right? They're looking to try and understand the traffic in a particular day for a specific author, for a specific content area of article. They're looking for the top performing articles over the past 2, 3, 4 hours. Right? They need to know about social engagement trends. What's getting picked up on social media with a little bit of a kick could go viral. And then the developers who are building this content, they need to know about their API query performance, right? So they're calling back to a set of APIs. They need to know how that's performing. They need to know about exceptions. So all of the exceptions get swallowed because we don't throw them back out at users if they just log them, right? They need to have access to that information. They need to know how to maximize the cache hit rates. The way that we've been doing data at AOL for the last few years wasn't working, right? So I joined AOL specifically to work on this project, and it was actually kind of an interesting experience for me. I'd never had this happen where I had been talking to my new boss on the phone for like the 3 weeks while I was changing jobs. And I knew exactly what I was going to be working on when I started. And in fact, when I got to the office on the first day, I got my CD so I could log into the network. And then immediately started working on answering a question. Which is that question I asked at the beginning of the talk. How would we let editors test how well different headlines perform for the same piece of content? So I'm not going to say that multivariate testing hasn't been solved. I mean, there's lots of different ways you can do multivariate testing. The difficulty here is doing it in a pseudo real-time fashion that doesn't require a lot of overhead in terms of development time and engineering time. You want to let editors create tests on any different kind of variable that they want to get that data back very quickly, right? So I'm going to tell you about the process of building a real-time data pipeline and how I did it by only failing 3 times. So I started immediately on my first day working on a proof of concept. The streamer over here on the left side is, if you think back to that architecture diagram that I showed you before, those are the real-time streamers, RTH streamers that were up here on the right side of the screen. We have a receiver piece of code that's going to connect to that HTTP API and start receiving all that data that's getting vomited at it really quickly. And then my initial thought was, we'll pump that into StatsD. StatsD will go into Elasticsearch. So what does this look like from a logic standpoint? We have a streaming HTTP client. This is done originally in Node.js. So anybody familiar with Node.js and streams particularly? Okay. So this is just a native Node stream. We collect this data. The new record comes in. So basically, we're looking for line endings and cutting off each line. generating an event for that, and then we have event listeners that pick up that record and generate a stats-D record. And those get pushed back out. One of the things that we really wanted to do, because we didn't know what kind of data we were going to want to extract from this, is have the ability to have these listeners that actually go in and extract information be very, very small and self-contained. This is the only piece of code that has remained unchanged since the proof of concept to production. Right? This is just parsing out a user agent out of that string. So it's looking for this key inside the raw record and then parsing it, and then returning a key containing the parsed out user agent, right? So it took me 7 days to build out this proof of concept, and in the end, what I had was, I wish I'd taken a video of this, I took this on my 7th day at the company, was this map of the world. And we were pulling out the geographic location. You can see this is the location field down here. And as the countries had more and more traffic, we colored them darker and darker. So not really very useful, but it kind of proved that we could do something at least somewhat meaningful with this stream of data. The proof of concept, though, was nowhere near where we needed to be. So remember I said we were collecting 15,000 records a second. That's an average, goes up and down. 300 per second with this receiver, which means that we need at least 70 in order to run this in production. And then stats-D actually imposes a bunch of different problems. So we get these huge payloads, and they're very, very rich. They might contain the location of the user. If they're a person who maybe has not turned on all of the privacy settings in their browser, we might have their what we call an unauth ID, so like just a randomized string that identifies that user as someone who's looked at our different properties. So, an ad tracking cookie. Right? We might have that information. We might have information about their device. We might have a lot of very, very rich information. When you put this into stats-D, it all gets broken down into numbers. And there's no connection. You lose those connections between the data. So instead of, for instance, knowing that someone in Salt Lake City looked at this piece of content on an iPhone, we know that someone in Salt Lake City looked at this content. We know that someone on an iPhone looked at this content. Right? You lose the connection. It was after this that I kind of realized that in order to I guess I am quoting myself, and yes, I am that much of an idiot. That to do this efficiently, right, to have a real-time data pathway, you need to have a network of transits and terminals. This is terminology that I made up for myself as I was trying to figure out how to build this. And I wanted to make sure that we didn't have single nodes acting as both transit and a terminal, because I was noticing that with stats-D particularly, like it. If you're not familiar with how stats-D works, it collects data and it aggregates it in memory, and then when it reaches a certain point, it pushes it out to a back end, right? It wasn't having it perform those two roles of both pushing data, moving data from point A to point B, and doing math on it was really inefficient at this scale. So when I think about transits, I'm thinking about things that are short-term, in-memory, volatile storage where data doesn't live for a long time. Right? It's data that's only going to be around for a couple of fractions of a second, that's on its way someplace else. And then terminals being places where destination goes to either be stored, destroyed, or sent on to do another transit to something else. One of the first decisions that I had to make here was what to use as a backbone for that data pipeline. And obviously stats-D was not going to work. So I looked at Kafka and RabbitMQ. Who's familiar with Kafka? A couple hands. RabbitMQ? Okay, a few more. So Kafka is a pub/sub message router. It came out of LinkedIn a few years ago. It's been under Apache for a while. The big, kind of like the big selling point for Kafka is that you have messages all are guaranteed to be delivered in the order that they were sent. Right, so it's a fault-tolerant, persistence-oriented messaging queue. RabbitMQ, on the other hand, which is basically the most common AMQP implementation, was I think it's by Pivotal. It focuses on just general-purpose messaging, routing, and it uses federation, so you can have different rabbit clusters that are federated with very high availability, right? So when you think of the requirements of what we were trying to do, those payloads that we come in, I don't really care about the order that they arrive. It doesn't really matter. Due to the nature of JavaScript being asynchronous, we might get them in a different order than they actually, than the order in which the user actually interacted with them. That's why they're timestamped, right? So they're timestamped out of a microsecond. So we don't care about that. Some of the data loss is really acceptable because we're talking about billions of records, right? So you're trying to do statistical analysis of billions of samples. Losing 10,000 or a million or 10 million of those records really isn't going to change the final outcome very much. We knew that particular consumers of the pipeline might only want a small subset of the data, so routing was very, very important. We needed to route that data to different data centers and also to AWS, right? So right now the company in general is in a transition from our own data centers into AWS, so a lot of our applications are what we call in purgatory. They have one foot in both, and so going across that bridge is important for us. And also our applications at AOL, we generally, if it's not Java, it's PHP or Python. We have a couple of things that are in Ruby, C# here and there, but generally we are Java, PHP, or Python. So having support for the languages that we use is really important for us. And that's really why RabbitMQ went out in this fight. RabbitMQ offers federation, so we can actually set up routing logic to say that for these records, we want to send them, just them, over to this other RabbitMQ cluster that lives in AWS. So we're going to subset a small amount of data, send it over this VPC connection that we have to AWS. It supports that kind of routing natively, so you don't have to write application code to do the routing. It supports all the languages that we use it, and obviously we're a huge company, so the fact that there's another big company like Pivotal behind it is a big selling point for us. So in version 1, you'll notice that SASD is gone when RabbitMQ is in this place. I made some other changes, and these are application level changes. So I was using the observer pattern. I was using the generating events for new records that were coming in off the stream. I moved away from that for data processing to using a single in and a single out event. Right? So Node.js is really, really blazingly fast, but it does have memory issues. And when you generate a ton of events in Node.js, what you're doing is you're creating a ton of memory. You're allocating a ton of memory, which can cause some serious performance issues. And you can probably tune around them. The V8 engine is very, very tunable. But node streams have this really cool back pressure mechanism in them, so it's nice to be able to just let that back pressure mechanism just regulate the input rate, which is what it's meant to do, instead of trying to get happy with how V8 is allocating memory and how it's handling bursts of event creation. From a logical standpoint, not that much has changed. So we still have a node stream coming in. We're still cutting off records and new lines, but now we're pushing them onto a process chain. And they're going for each subsequent transformer, starting as a raw record and then coming out as an enriched record at the end, which then gets pushed in. So this was really great. This worked well. Immediately while I was in development, I started noticing a problem. I started having to write code like this, which is to say, pulling the first record off of an array, and then inside of a loop, and then trying to figure out which of these is faster than the other. Now I can't remember off the top of my head which one. I believe this is like ridiculously faster than the one on top. I don't know if people with that makes a difference, but when you start looking at like the performance of an operation on an array in a loop as a big indication of how much hardware you need to allocate to run an application, you've done something horribly wrong at the architecture level, right? I did get the message rate up to 600 per second, which is double the proof of concept, right? So that was good. And it cuts the number of receivers down to about 35-ish. right? But first of all, it's having to micro-optimize all of this code, dealing with actually just kind of constructing these buffers coming off the stream. And because I was doing this, I kept running into really weird encoding issues. So, for example, Engadget is a global property. They have editors who work in China and who work in Japan, and who write articles in their word processor. And then whatever encoding that happens to be in, they copy and paste it into our CMS, and the database goes, okay, I'll try and shove that into Unicode, I guess, into UTF-8. And then when we get it, there's a null in there, and now the application falls over, right? So started adding lots and lots of code to deal with weird encoding edge cases that were causing issues, right? I want to point out that this is not a problem with Node. This is a problem with me. Not knowing how to use a tool doesn't mean it's a bad tool. But I need to take it serious at this point. First of all, I said before that I had this kind of like idea of separating transits and terminals, separating that concern of moving data versus performing operations on data. And that receiver that I have is doing both of those things, right? It's receiving the data, but it's also editing it, it's routing it, right? So I want to turn that receiver into a simple transit that just consumes the data and pushes it onto the RabbitMQ. And it would be nice if we could do some very high-level filtering. I also wanted to have something that could do static and dynamic optimization, multi-threading, something that could handle these very large, very volatile data sets in a clean way, right? So I had a couple of options for picking the stack for this receiver. I can stick with what I was working with. Node.js is really, really simple. I know it well. It's easy to distribute. We have a lot of infrastructure for deploying Node.js applications at AOL. I could use Go, right? So Go is really cool if you guys aren't familiar with it. One of the big features of Go is that it has these Go routines, which are like native pseudo threads. They do really, really nice multi-processing. Use Rust, which is basically C++ that doesn't kill your soul. Java, which has really, really great static and dynamic optimization and memory management utilities, and pretty good multi-threading in Java 8. And with C or C++, which is got some good libraries for concurrency and stuff like that. For Node, there was really no way that I was going to be able to tune it to the point where we wouldn't need just too many instances to make this run in production. For Go, no one on my team has ever done anything with Go. I've done a couple of small things, like dealing with like little chunks of data, but never a complex application. So it would have been a learning process for me, and it would have been a learning process for them. Same thing goes with Rust, except when I brought it up, it was like, oh, I learned Rust. Java, I gave a talk at PHP conferences, I was afraid everyone would be mad at me. And then I really, really don't hate myself enough to do C. I think it's important when you're designing applications to understand other people's visions before you really get comfortable expressing your own. When I first started tackling this, so that whole data management system is managed by another team that's part of my organization. But when I told them what I was trying to do, they told me, you're probably going to want to build this in Java. And I said, no. It's 2014. Java is, it's a Node.js world, let's be honest. Everything's in Node.js. Node.js is best thing in the universe, greatest stack that has ever been built by humankind. Why would I ever work in Java? I had to tuck my tail. I ended up building this in Java. So let's look at version 2. We still have the streamer and the receiver. Now this receiver is now the Java piece. We have RabbitMQ, and then over here we have what I call the processor router. The processor router is essentially all of that editing logic that was in Node.js just moved up to the other side of RabbitMQ. So essentially what's happened here is I'm using this RabbitMQ infrastructure as a buffer. So we're reading off the stream, we're doing some very light amount of filtering here, and then pushing it onto another RabbitMQ farm, then picking it up and then actually doing the edits. So we've broken the dependency for this code, this editing code, have to be able to handle the full stream that's coming from the data architecture. Right? So this is Java code. It's clean. I'm just showing this to kind of show that if you haven't done any Java in a while, it's changed. Like it's not what you're like what we all think of, like 9,000 line XML files. So essentially what we're doing here, we're just building a stream reader here. So we're creating, I was taking a screenshot of the development version of this because this is not actually hard-coded. So we generate a number of threads, we start them up. And then as data gets pulled in, we push it onto the threads. Right? We push it onto the threads. And then what the threads are simply doing is taking that packet of data. It should be valid JSON, so we just try and deserialize it. And if we get a good object, we pass it on. If we don't, we drop it on the floor. So that's when I say we're doing some light filtering. We're just filtering out, like if somebody just goes in there and says, what's b.aol.com? I'm going to post just, a Shakespeare sonnet to this b.aol.com. It comes through the stream just fine. We can actually just drop it on the floor at that point. I kind of feel like the application looks like a bunch of ketchup bottles. Right? So we have an input. We have all of these threads that are basically just wrappers around linked lists in memory. So the data falls in on the top and it gets pushed down the bottom to the network. From a logical standpoint, this diagram still looks pretty similar. Right? So we have data coming out over the stream. We cut the new records. It goes into a queue. To those threads, the work threads, process the records, and then push them out into RabbitMQ. So, with this new version of the receiver, I got a little bit of a performance boost. Yes?
Can you go back to like the decision of using Java versus Node? I'm not sure I understood that part.
Right.
So was it like you couldn't have multiple Node.js instances, and then like what was the reason for using Java versus the multiple instances of?
Essentially, the real issue with Node is that we couldn't find a way to both process enough records per second and keep the memory utilization to the point where things weren't in swap, right? So if we wanted to keep, say, the Node process under 8 gigs, we had to severely limit how much data we could pull in. If we wanted to just open up the floodgates, we kept kind of bumping into swap, and then once you fall out of memory, you're dead. But yeah, so the Java receiver it pulls 2,600 records a second. We only need about 10. Actually, we have about a dozen in production, so a pretty close estimate. The validity filtering is almost free because actually the JSON parser in Java is really efficient. And then the processor router service is free to only select the messages off the stream that it wants. It doesn't have to receive everything. They're going into RabbitMQ, and if nothing pulls them out of RabbitMQ, they just get dropped on the floor after a couple seconds, right? So it eases the amount of data that's getting pushed into that processor, the Node.js application, right? So big win. This is doable. This is an application we can build. Yeah?
So if I understand what you just said, you use your RabbitMQ as a temporary cache.
Essentially, yes.
Only it's time dependent. You don't process a message at a certain time until RabbitMQ to feed you and go out.
Yep.
Nice.
Exactly. So it's a sync. That's what I was saying.
And it solves your big data handling.
Yep. Exactly. So so that's the pipeline. I mean, it's really not that complicated. It's really just RabbitMQ and a little bit of application logic wrapping around it to push data through it. Without the consumers, this pipeline is useless. So really what I want to talk about for the next 20 minutes is the stuff that we've built on top of the pipeline. The real-time analytics service is the first thing I want to talk about. So this is actually doing math with this data that's coming through the stream, right? So the goal is to provide near real-time statistics for the editorial staff. Allow evaluation of arbitrary fields, arbitrary values, and to provide an interface for the developers who are working in the publishing stack. So those are the PHP developers, right? That's where Elasticsearch falls into place. And I think this kind of was this big ball over on the right side. Why Elasticsearch? So is anybody not familiar with Elasticsearch? Awesome. Elasticsearch, I don't give a damn about the search stuff, what I'm using it as a high performance NoSQL database. It has high availability via clustering. It's rapid data center aware. And it's got a really, really nice query. Well, I don't want to call it nice. It has a very powerful query DSL and nice bindings for PHP and Node and all the other languages that we might want to use, right? Elasticsearch lets us do cross-regional federation in AWS. Right? And it also has native clustering, right? So we have our data gets pulled in and then it kind of gets clustered across different nodes. If you add nodes, you can rearrange how the clusters are allocated, so it kind of lets you create easily expandable self-healing search clusters. All right, so we're already using this in production for, obviously for search. So I mean, this is just some query DSL to search for Miley Cyrus. This is Cameo.com. If any of you have like 17-year-old daughters, they're probably really into Cameo.com. This is what an analytics query, this is an actual live analytics query, looks like for multivariate testing, which we talked about before. I'm sorry, this is not multivariate testing. This is for a traffic dashboard that we run, right? So we're looking at particular posts. So we get these posts by looking at information we have on what's popular right now. And then we're just taking this data in, and we're doing nested aggregation. So we're trying to see, first of all, what the source of the data was, and then looking at search terms, looking at the referrers, see where the referrers came from. So we can generate stuff like this. This is from Engadget.com. Looking at some of their popular posts and looking at page views in the last hour, and then social search with internal and other referrals. So internal being referrals from other AOL properties, and then obviously social search. And then other, generally speaking, just the people like randomly hitting the page, or for some reason there was no referrer in the headers. Like I said, it's got a very simple interface for all the different products, all the different stacks that we use, right? So this is generating, this is indexing documents in Node.js and then pulling them out in PHP, right? Off the screen a little bit there. And then pulling them back out in PHP. So very, very simple, right? So multivariate testing, which was the first problem that I talked about, when we want to let editors test the performance of a headline, but maybe not just a headline, any discrete content element, anything that gets put on the page, we can identify as a variable in a multivariate test. We want to let them be able to start, stop, and evaluate their tests without spending any developer time. Right? So what do we need to do for multivariate testing? We have to assign new visitors to a test group. We do this by giving them a cookie. We have to inject test markers into the beacon payload. So I showed that very, very early on. I showed you the kind of like multivariate test marker. Just a little string of data that gets pushed into that beacon payload. And then we do a click-through rate for page views, right, with the test markers to calculate performance. So we look at kind of what that looks like. So we have a test population identifier, so which group was this user in, and then what was the test. So these tests are stored in the database somewhere. So then we can then look and see for all regular page views. Let's do a nested aggregation based on click type, and then look to see if they have a multivariate stats field. Get the test ID, and then look for the hashes and then the clicks. All right. So then we can take this, pull this into PHP, right? And we can do some very, very complicated mathematical formula to figure out the click-through rate. Right? And it lets us have something like this. Right? So they can come in here and they can say for this, we're going to have these different headlines, for example, and then they can weight them however they want to weight them. What's important about this is that an editor can come in here into this user interface. They can create this, and then within 5 seconds, a click shows up in their statistics. So we have end-to-end 5 seconds from someone actually clicking on a link to that number being updated. Now, granted, they're not going to see that number. Like, it's too small of a value to actually shift the number, generally speaking. But the numbers are coming in immediately. well maps. So my boss is a really interesting dude, his name's Christoph. He always has this idea of like native real-time maps, right? So what we did was build a small WebSocket server that's going to consume a small stream of this data, actually select only a small percentage of the data, and then push it onto a WebSocket stack. So we're going to fire events to a WebSocket connection. Like this. So we have the input, some goes out to analytics, some goes out to visualization. Just write some very simple D3 code, right? To create a map projection, and then when we get a new event, draw it on the map. And it ends up looking like this. My boss loves this. And he's like, oh, that's so cool. I'm like, yeah, it's a map of the English-speaking population of the world. Sorry, I don't want to lie. It's also the Korean-speaking and Japanese-speaking population of the world. Two big popular and Gadget sites. But there's actually a lot of value in here that's, I think, difficult for me maybe as an engineer to understand, is that people have this animistic connection to their work. And it's one thing to write an article. It's another thing to look at numbers, to say, oh, 10,000 people looked at my article. It's another thing to look at a map like this and see like this real kind of pulsing live visualization of people looking at your stuff that people really connect with. I tried to make this a little bit more useful. I color-coded the dots based on the property. And there's nothing really revolutionary in here. Like we see the green dots are daily finance, really popular in places where they have stock markets in New York, the West Coast, London, really, really big. Autoblog, for some reason, was like really huge in Eastern Europe and Russia, but really into cars there. Embeddable visualizations as well. So like this is a very popular visualization that we can actually embed inside the CMS. So we can have this sitting there next to a post. And I won't call this a graph. I call it a visualization because if you'll notice, there's no numbers on these axes. Right? This information is completely divorced from any real data. But what it does show is that the data is actually people actually interacting with their posts. So they click publish, and then in a few seconds, you start seeing this wave. You start thinking, oh wow, a lot of people clicked on this, really like network glitch. I mean, it's very silly, but it still works for them. So I think I have a minute or two left. The last thing I wanted to talk about was live profiling. So I don't want to leave out the developers for these sites, right? When we're writing JavaScript code for stuff, we might use the Chrome Inspector Profiler, use your debugger in your IDE. They don't really have that because they're working inside a kind of a walled garden, right? So we wanted to let them be able to look at that kind of profile information in their code that they're writing, right? I'm going to jump through some of this. So essentially what they're doing is they're writing code. It's a DSL that's based on Twig. It's called CodeWall. It's actually really interesting. I tried to get the guy who created it to give a talk at a PHP conference. I think it's really interesting. Essentially, they're writing code. What this profiler lets us do is the devs start the profiler session. They can do this on a development machine, or they can do it in production. We're going to tag information that we're already generating, profile information that we're already generating, with that session ID. And push that out. We need routing to push those messages into a profiler service that the developer is connected to using a JavaScript application. So what they start seeing is, and again, they can do this live in production, they can start seeing a waterfall of how their application is executed. Right? This is a great example because they have some really, really slow HTTP calls. And the last thing that we built very, very briefly, cross-platform eventing. So like I mentioned, we have Java, we have Python, we have Node.js, we have PHP. Those are our primary stacks. How do you fire an event in PHP and have that turn into a native event in Java or a native event in JavaScript, right? So we're allowing, in this case, for example, the PHP is built in PHP, the CMS is built in PHP. We use the Symfony event dispatcher for doing events and observer stuff in PHP. We allow those events now to be forwarded over the data pipeline and picked up by listeners in any language that's adopted this pattern, right? So here we have code in PHP where we're actually just going to dispatch an event. This is actually the dispatcher. When we dispatch, we're just checking to see if the event is forwardable, and if it is, we push it out into AMQP. Right, and then in a Node.js instance, for instance, running in AWS, we pick up that event, and we actually use this in production for doing search indexing. So, to summarize, we're processing 1.3 billion events a day, using RabbitMQ to route data to microservice consumers. We're driving a real-time analytics platform now that is 250 gigs of raw data per day, so that's that Elasticsearch cluster, and visualizing about 1.3 million events per day on wall maps, stuff like that. We're doing live profilers for developers of about 50 different properties, and we're indexing about 10,000 updates to different documents a day. This is all going back and forth in the same pipeline. It's built in Java, Node, PHP, some Python for the load balancing and routing, and then obviously we do RabbitMQ, Elasticsearch, and Vertic on the sort of infrastructure stacks. For 2016, embeddable visualizations is something that we have now. We want to expand that. Building out these on-demand stream filters with Redis, time series bucketing, so we actually have another interface you mentioned with API, you can get that directly out of Redis. And we're pushing more into the area of doing real-time predictive analysis. We're actually looking at this data, pushing it through our machine learning platform, which is called Relligence, to actually do that machine learning instead of crunching the entire database, crunching this data as it's coming through the stream in pseudo real time. So that's all that I have. I think we ran right up against time. Do we have time for any questions?
You know, so we're coming up to lunch, so
Oh, okay.
so people could stop and talk, stay and talk to you if they want. Meeting.
All right. So yeah, if you guys have questions, just come up and I'll be happy to talk about this. Otherwise, thank you.